Okay. So, next speakers is Dr. Panagiotis Barkoutsos from the IonQ company. His talk is about quantum technologies at IonQ. Please.
Great, and great pronunciation of my name. I know it's difficult. So great to be here. I know it's late, and I know that most of you had a long day. So bear with me for some time while I'm talking to you about IonQ and what we are doing. So we're a quantum computing hardware company. We are focusing on building quantum computers and how we can actually use them. So we're in the field of the full stack quantum computing, and we're super interested into finding ways to use our quantum computers, as I'll show you today. So our goal is simple. We want to build the world's best quantum computers to solve the world's most complex and impactful problems. Okay, a lot of big words. Best quantum computers, most complex and impactful problems. So this is the goal of the whole quantum computing industry. This is what people want to do in terms of doing quantum computing. So we want to find ways to leverage the new devices, the new machines, and make sure that we are doing something that has impact in the industry, the socio-economic world, and in general, we are not just spending a lot of time and a lot of resources and a lot of effort into building a device that is not used. What are we doing as a company? What is IonQ doing as a company? So first, some information about what we do and what we're doing in terms of road mapping and in terms of developing things for us. So first of all, we promised a roadmap. We were able to deliver on this roadmap. For 2024, we were already 12 months early in our roadmap, meaning that we are ahead of time, and this gives us a lot of lead time to experiment and develop new devices, new techniques, and new technologies in general. Right now, we have 36 algorithmic qubits, and this is one of the biggest industry-leading cases because we are not focusing on only scaling in the number of qubits, but we are actually focusing on scaling algorithmic qubits. Algorithmic qubits, you can think of it in a way as meaningful qubits that can be used for different quantum operations and can be directly used in the full capacity in our computer. We do have a lot of ideas about error correction. We are thinking a lot about how can we do error mitigation in the near term, but at the same time, how this can scale in terms of error correction. We do have some ideas about low overheads, so how can we really make error correction more efficient for our devices? And what we do is that we try to exploit all the capabilities that ion trap-based quantum computers are offering for us. We are available on running in our devices via all the quantum software development kits. We have a lot of integration with different devices. We are available in all the hyperscalers, and you can find devices from IonQ and run very easily. No matter what code you are using, you can definitely use an IonQ as a backend. Our devices are data center ready, meaning that you can just integrate them directly on a data center without the overhead of having to do a lot of electronics and a lot of very complicated designs that other modalities require. And we recently have a European effort, so we deployed our first quantum computer in our Basel Innovation Center, where actually I reside too. And we noticed that we are able to really make devices again and again, and this is something that is quite interesting, and we are really happy to see this. Eventually, why we are doing it, and this is a very fair question to ask. The simple answer is that we are doing it because we noticed that ion trap-based quantum computers, except the historical technology development, they are really good in terms of high fidelity and connectivity. So we have very good devices that can be used in a very efficient way. What this use means? This use means that eventually quantum computers will be able to really be used for commercial applications beyond what we can do with the current classical computers. So the new computing paradigm will really unlock capabilities that we don't yet know and we have never seen. And this will give us a lot of insights in terms of computation beyond the classical limit. We heard today a lot about quantum advantage. You heard a lot about how can we go beyond in terms of time, in terms of speed, but this is something that we need to be able to really see materializing in the near future. Beyond computing, we recently started a big effort around quantum networking. This happened with the acquisition of Qubitech, a US-based company specializing in quantum networks. And we hope that via quantum networking effort, we will be able to go towards distributed computation and at the same time secure communication in order to go beyond what classical networks can offer. So I'll say a couple of words about it in the very end. Okay, so in terms of the computation, our qubits, as I mentioned, we are based on ion traps, and our qubits are having some advantages comparing to other modalities. The main advantage, and one of the biggest ones, is that actually we have identical, naturally quantum qubits because we're using ions, so we're using elements. What we do is that we have a cloud of ions, we load them in an ion trap that looks like exactly the one that you see on the right side here. And these ions have long coherence and qubit lifetime, so you can do a lot of operations without the need to change or reset the ions. Our 2-qubit gate operations have a very high fidelity, very high native fidelity, and this all comes because of the controls and how we are implementing the gates. Okay, it goes without saying that we have a universal gate set, so we are able to do universal quantum computing, and at the same time, our ions are reconfigurable and highly connected. Highly connected means that we can implement any arbitrary connectivity within the chip because we have all-to-all or any-to-any connection between our ions. Eventually, another advantage that we're seeing in the architecture that we have chosen to build our quantum computers on is the fact that it can work in room temperature. What it means that we don't need to have cryogenics, we don't need to have very elaborate designs with very scarce resources in order to reach the millikelvin regimes. We can operate in the room temperature. The reality is that we do have some very simple fridge. So this takes us down to temperature, mostly to shield ourselves from disturbance from the environment, but this is nothing in the order of millikelvin. So here we're talking about few kelvins, in certain cases over 20 Kelvin. Okay, so where do we stand and what is the roadmap that I mentioned before? So right now we are in 2025, where we are expecting to have our devices called Tempo. If we go back a little bit in time, in 2019, we promised to have our first generation, which was the IonQ Harmony devices. And these are devices based on an element that's called ytterbium. And we built a couple of devices on Harmony generation, and these are all now deprecated and not in the cloud anymore. The simple reason is that Harmony was working very well until we got a more performant device, which was called Aria in 2021. We also have 2 devices that are both available in the cloud right now. Later, we had Forte, which was our first commercially available and higher performance device. And in 2024, we had our first Forte enterprise generation devices that are really enabled for hybrid services and data center ready. This means that one can deploy these devices directly without the need of having an experimental setup or having someone that maintains these devices. Okay, so now we are expecting to have, by end of the year, announcements around our newest systems, which is called Tempo. And the goal is to go over 64 algorithmic qubits for this particular setup. Up to now, we were able to over-deliver our expectations, so hopefully 64 was an estimate that we did, and then again, we will be able to over-deliver on this. So a comparison with other available quantum computers. So this is a third-party comparison, and this is based on the algorithmic qubits benchmark. Our devices, Forte and Aria, which are the 2 previous generation of devices that we have, are on the very left, and we compare them with generations of IBM and Rigetti devices. So algorithmic qubits are benchmarked based on certain algorithms like Hamiltonian simulation, phase estimation, quantum Fourier transform, amplitude encoding. So we just take a bunch of near-term algorithms, we try them, and then we see how this goes in terms of circuit depth, which is what you have on the x-axis, and then circuit width, so the number of qubits on the y-axis. You see that the window that our devices are operating is significantly bigger. And what we do is that in principle, we run the algorithm until we have non-meaningful results produced. So we want to saturate the meaningful results and see up to what level our devices can perform. In our case, we were able to go in circuit depth in the order of close to 1,000 gates, maybe 500 gates, with up to 36 qubits in order to run this particular algorithm that we used for the benchmark. Okay, considering the time, I would like to talk a little bit about quantum advantage and how are we going for quantum advantage. So for us, quantum advantage does not reside in a single metric. Quantum advantage needs to be a combination of three different elements, which is performance, scale, and enterprise-grade quantum computers. We are working actively in all the three domains in order to be able to say that we are scaling our quantum computers in the right way and we are growing our user ecosystem. In terms of performance, we are really pushing the barrier of high qubit quality. So we want to be able to have better and better qubits, higher fidelities, and at the same time increase our gate performance. So we need to see how we can make our gates faster and better. A point that I already touched upon is the error handling, where we are thinking about how can we do error mitigation in the near term and error correction in the longer future. In terms of scalability, I mentioned that our devices are having arbitrary connectivity, so all-to-all connectivity, but at the same time, we're thinking a lot about how can we do compilation, how can we reduce circuit depth, how can we really go for higher connectivity, even between quantum computers, so distributed quantum computers. Enterprise grade, it's mostly around deployability and availability. So we showed that we can actually deploy quantum computers in other locations by our latest deployment in the Basel system. And at the same time, we noticed that we can have quantum computers that are available for in-house. At the same time, we want to increase our availability via cloud, so we want people to be able to access our devices in the cloud more frequently and easier. In terms of applications for commercial advantage, we have identified certain cases that we work with different partners, and I'm going to talk a little bit more about in the next slides. But here, just highlight some that are already published and that are already well known in the community. So we're working with Airbus on optimization problems. For example, the case of supply chain optimization. We're working with Oak Ridge National Lab in the US about energy infrastructure improvements. We're working with a recent partnership that we started with AstraZeneca, so the pharmaceutical company, where we are thinking about how can we do drug design and modeling of different diseases. We are working with many other, okay, let's also mention ANSYS, since it's one of the strongest partnerships that we recently established, where we're thinking about how can we do simulation modeling for engineering cases. So let me walk you through a couple of recent applications that we have developed, and these are of critical importance. And here we start with the GPU acceleration workflows, which is a work that we did in between us, ANSYS, AstraZeneca, and these are some of the partners that we have. So we worked on quantum lattice Boltzmann method for computational fluid dynamics, quantum imaginary time evolution for optimization, and also auxiliary field quantum Monte Carlo for chemistry. For the first one, on the computational fluid dynamics domain, what we did is that we were able to speed up to 50 times. Actually, we were able to reduce the number of gates up to 50 times, leading to a speed up in the quantum circuit that we are doing. The use case that we have examined was relevant to the 2D fluid transport, and this was mostly implemented via CUDA-Q, so the NVIDIA quantum language, and this was a partnership between IonQ, ANSYS, and NVIDIA. Another application was mostly about simulation of blood pumps and roof crash. That's also another CFD problem, where we would be able to see up to 12% improvement over the classical heuristics on a 2.6 million vertices and 40 million edge graphs that in order to simulate the pumps, so the heart pump. Eventually, the last application that I want to touch upon is the acceleration of drug development with enhanced simulation for drug synthesis. This is a work that was done between ourselves, CUDA, AWS, and AstraZeneca. And there we were thinking about greater efficiency and accuracy, about going to more precise predictions and minimize trial and error in synthetic process design. This was something that was very interesting for the pharma company and the pharma industry because these are really costly processes and they are going to give us a significant speed up in the time to solution. So finally, I said that I'm going to talk a little bit about quantum networking, and in principle, what we are thinking is that we're thinking of how can we go from a pure quantum machine to a very well connected network of quantum machines. We're thinking about photonic interconnects, and we're thinking about ways that we are actually going to create this quantum network. So more information on this topic will come soon. Hopefully by end of the year, you will see a lot of development coming from us on this topic. Thanks.
Thank you very much for your very nice presentation. Please, comments and questions. So my honest comments that I believe that you presented the another platform for the quantum computing, yes, because today we hearing the presentation about the superconducting platform for quantum computing, and this is another platform, and which is commercialized, yes. So this is very important. Very nice results, both scientific and the commercial results, I believe.
Yeah. So we like to call it different quantum computing modalities. So it's ways that one can implement the qubits. In our case, we are using ion traps based on ytterbium, as I mentioned. And we are working on extending also to other elements. But definitely this is something that is available via the cloud and also for in-house purchase if there is interest.
I believe yes, but the application yours yes, but if I understand as today also yesterday and today maybe you need to obtain some collaboration, some research, some activity which where is need to solve some mathematical problem which will be helped by your computer. So I believe.
Okay.
This your
So understanding the applications domain is very critical because in principle any problem that you want to map in a quantum computer would require a totally different approach. So if you want to go for an optimization problem, people are talking a lot about how can we actually encode optimizations. A quantum computer, especially on the near term, is good on estimating one can say energies. In the end, any problem can be mapped into a Hamiltonian and then estimate the different eigenvalues of this Hamiltonian. So how you encode an application to a problem definition, this is something that every problem would have a different mathematical formulation and different way that you need to approach it. So this is something that we are also doing and we are actively working on it, but we are always doing it from the scope of how can we actually demonstrate state-of-the-art device used for relevant applications.
Yes, my suggestion is that I believe you need to stay in more close contact with the theoretical researcher, theorists. They can help you because they create the theory, and as I understand, the theory should be completely change the philosophy of the theory in order to use the quantum computing. Yes?
Yeah, definitely. We need to change the way we are approaching. It's a new computing paradigm. And we don't claim that we can do things on our own. So in principle, everything here becomes synergetic because people coming from operation research can tell us a lot about optimization. People coming from chemistry can tell us a lot about the chemical applications. So definitely this is not a field that one can excel on its own. So we really need to be able to work together and co-develop these applications.
Yes. So another question and comments? Thank you very much again.
Thank you
very much.